Our next speaker today is a true AI full-stack capacity. Early on in her career, she designed the next generation GPUs at NVIDIA. Then she developed high-performance inference kernels and quantization kernels. And now she is an engineering manager at PyTorch, the PyTorch core performance team, where she is responsible for the latest and greatest PyTorch features and, of course, for the people behind this. So please join me in giving a warm welcome to Supriya Rao.
Thank you. Hey, folks. Really excited to be here. Today, I'm going to be talking about quantization and sparsity, specifically through the lens of what we've been building for this at PyTorch. So we've been building this library called torchao, which stands for PyTorch Architecture Optimization, which is a library for quantization and sparsity that's easy to use, fast, and composable with the rest of the PyTorch ecosystem. So it works great with other PyTorch primitives like torch.compile and other distributed primitives like FSDP2. Instead of just being easy to use and build on, it also provides state-of-the-art performance for both LLMs and diffusion models on NVIDIA GPUs. So the main features that torchao provides are quantization and sparsity. Quantization enables you to run your model at a lower precision by quantizing your weights, activations, or gradients to different D types like int8, int4, FP8, NF4, etc. While sparsity works by removing parameters from your weights so that you can run your model faster during inference. And using these in PyTorch is a simple one-line API where you call the quantize or sparsify API, pass in your model, and pass in the specific technique you want to do. So there were a few symptoms that we observed in the open source community that really inspired us to create torchao. First is that getting a technique like quantization right is challenging. And even if you get it right, writing performant kernels for this is hard unless you're a CUDA expert. Moreover, once you get these techniques working, getting it to work with the rest of the PyTorch stack, like distributed training, is non-trivial. For example, let's say you want to run QLoRa with FSDP or FSDP2. Also, you have all these optimization techniques. There's always a question of how do these techniques compose with each other. And lastly, we all know and love torch compile and think it's amazing, but we don't know how to use it with these optimization techniques. And so our vision with torchao is that it should be trivial for you to quantize or sparsify any part of your model to whatever data type that you want, whether it's your activations, your gradients, or your weights. Run it for training or inference on a single GPU or 100 GPUs, all in native PyTorch, and all without sacrificing any performance. So how do we do this? In torchao, you can write your code in pure Python, and that gives you really fast development speed, and you can take advantage of torch compile to generate fast performant kernels. And you also get sort of like the composability support that you see in this diagram. In some cases, the compiler might not be performant enough, so we also provide ways for you to build, package, and ship custom Triton or CUDA kernels along with the library. So we think of ourselves as compile first, not compile fundamentalists. What this means is that we really build a tight feedback loop between torchao and the compiler, and we use torchao as a way to improve the performance of the compiler over time. So here's an overview of the quantization stack in torchao. At the very base layer, you have what we call the basic D types, and there are various signed, unsigned integers, and floating point D types that we provide support for. Sitting on top of these D types are the quantization ops and fast kernels. Quantization ops are operations that are used to convert tensors from low to high precision, while fast kernels are there in case the compiler may not generate optimized kernels. So now that we have these D types and associated operators, we can glue them together in an abstraction known as quantized tensor, and we have a support for affine quantized tensor, which is a subclass of a torch tensor type. At the top of the stack, we have the quantization flows, which is where most of our user-facing APIs live. So we have support for weight-only, static dynamic activation quantization, and various accuracy-preserving algorithms like GPTQ or HQQ. And the nice thing is that all of this is just in PyTorch without any external dependency. Under the hood, torchao uses tensor subclasses for most of its quantization flows. This provides a few benefits, the first being flexibility. So since it operates at a tensor level, we can quantize operations like functional linear layers, and we're not limited to just NN linear modules. Moreover, since it doesn't modify the graph, your model before and after quantization effectively looks the same. And this has an added benefit of making serialization and deserialization process really easy. So you can effectively load your quantized checkpoint into an unquantized model without requiring any prior transformation. All right, so this is how you would typically use quantization today in PyTorch or torchao. The first step when you want to quantize your model is to pick how you want to quantize it. And there are various parameters here that will influence your decision. First is whether your model is memory bandwidth bound or compute bound, depending on which you would choose weight only or weight plus dynamic activation quantization. Once you pick that, then you'd pick the D type that you want to quantize it to, depending on what your performance, hardware, or accuracy trade-off is. Once you pick these parameters, quantizing your model is just calling the quantize API with the specific technique that you want to quantize it to. This will give you an eager quantized model as an output, and if you want to make it go even faster, you can call torch compile on it to get even more performance. So what we noticed is that sometimes our users use our quantization APIs and their models actually run slower, which is not great. Why this happens is because quantization inherently has an overhead associated with it, and this overhead is amplified for layers with small shapes. So we built this tool called AutoQuant, which effectively leverages compile to generate micro benchmarks at a per kernel level and decide whether or not a layer should be quantized or what D type it should be quantized to. Another advantage of writing things in PyTorch is that these APIs are easily composable. We can take our int8 data type that we have and compose it with the sparse kernels to enable int8 quantization plus 2/4 sparsity to get even more speed up during inference. Okay, so let's look at some numbers here. This is Llama 3 at batch size 1, which is typically memory bandwidth bound. So a technique like weight-only quantization helps. And if you see on the chart on the left, as we reduce the precision of the weights, the speed up or the tokens per second increases, with the largest speed up being close to 2x for the int4 weight-only quantization compared to the bfloat16 baseline. Now we can also compose this int4 weight-only quantization with KV cache quantization and run the Llama 3 model with 128K context length in less than 24 gigs of VRAM on a consumer GPU. And writing KV cache quantization in PyTorch is just a few lines of code. This is written in less than 50 lines of code. And this is meant to be more as like a reference implementation that you can just copy-paste into your own model and enable KV cache quantization on it. On the training side, we also have easy-to-use APIs that enable you to do both computation as well as distributed communication in low precision, specifically for float 8, where we are seeing 1.5x speed up versus the compiled baseline. And under the hood, this uses a float 8 tensor, which is a tensor subclass type, and it leverages torch compile to generate the fast float 8 scaling and casting kernels, and also for fusing these kernels with preceding operators where applicable. With float 8 training, you also get autograph support and distributed support, so it works with distributed primitives like FSDP2, tensor parallelism, and sequence parallelism. So inspired by bits and bytes, we wrote low-bit optimizers in PyTorch in a few hundred lines of Python code. So we have 4-bit and 8-bit optimizer support in torchao. And it's pretty good, like we see 35% VRAM reduction on the Llama 3 model with them. And the performance is also pretty good. Quantization works great, not just for LLMs, but it's also great for diffusion models. For some reason, my video is not playing, but it's a cute video of like a little baby astronaut hatching out of an egg on the moon. All right, so yeah, so for diffusion models, we saw like a 53% speed up with float 8 quantization on H100s. This was generated by the Flux 1 dev model. And for Coq Video 5B model, for context, it takes like over 30 gigs to run it on the GPU. And with AutoQuant and compile, you can reduce not just the VRAM reduction by 50%, but you can also get like a 27% speed up because of compile. And as you can see, like these images were generated by quantized models, so the quality is pretty good as well. I want to give a shout out here to the Hugging Face diffusers team. They really like battle tested a lot of our quantization APIs and ran various benchmarks on diffusion models. So you should definitely check out their repo if you're interested here. So I spoke about a few techniques, but this is sort of like everything that we have today in torchao across inference, fine-tuning, and training. There's a lot more details like on the GitHub repo with benchmarks and API details. So if you're interested, basically feel free to check it out. The nice thing about torchao is that we've been able to experiment with a lot of interesting features in PyTorch. I want to call out a few here, which I think are really cool. The first is that Mobicham, who authored HQQ, actually added HQQ support in torchao in native PyTorch. So we not just have fast kernels, we also have good accuracy for those int4 kernels now in torchao. Vayuda wrote a lot of low-bit int D-type support using tensor subclasses in torchao, which really paved the way for us to invest more in low-precision inference now. Gonest has done some great work on int8 quantize and mixed precision training that's actually showing some pretty impressive results, which makes us want to invest more in this direction going forward. And Diogo integrated the 2.4 sparse Marlin kernels now into torchao, so you can see even more improvement in the performance compared to the previous int4 weight-only quantization numbers I shared with you earlier. And building on that, what we're really excited about next is the ability to run PyTorch quantized models on various backends. So a lot of what we've been developing on has been on NVIDIA GPUs, but for example, we'd love for us to be able to take quantized models and run them on your MacBooks or even on your phones. We've been talking about a lot of D-types, but we don't really have a full understanding of how these D-types interact with each other, so mixed precision quantization is also interesting going forward. And building on the work on float8 and int8 quantized training, we want to invest more in low precision quantized training, definitely. On the kernel side, so far we've not seen great performant less than 4-bit kernels. The compiler-generated ones are not performant enough, so we're really looking for more feedback here on how should we think about writing these less than 4-bit CUDA or Triton kernels. All right, so, okay, there's a little hard there. Torchao loves CUDA mode. Sorry about that. All right, so with torchao, we've been building all of these techniques as a community, most notably with the CUDA mode community, which has been a great way for our core team to get feedback on the features we build and really get a lot of interesting new contributions into the library. In fact, some of the CUDA mode members are really core maintainers of the repo now. I want to give a shout out to a lot of folks from the server, like Gonest, Vayuda, Coffee Vampire, Melvin, Andreas, Diogo, AIHD, Y4, and there are many more who've really helped us get to where we are today. And we're building this together as a community, and we really want to work with more of you going forward. So if you're interested in not building, but you want to try out torchao, you can also pip install torchao. And we are also fortunate enough to be integrated into some other awesome libraries like Hugging Face transformers, diffusers, SGLang, and TorchTune. So you can also use torchao through one of these frameworks. Yeah, and lastly, I want to sort of conclude by summarizing what we spoke about today. So I talked a lot about torchao, which is a PyTorch native library for quantization, sparsity that's easy to use, fast, and composable with PyTorch. And really, this one thing I want to take away from this is that it's more than a library. It's like a community-driven project. And we really need more feedback from the community for the project to continue growing. And we've seeded a lot of hacked ideas and projects together around the quantization, sparsity, and custom kernel space. So if you're interested in hacking on this, or if you want to make your first contribution in this space today, we'd love to help. So come find us. There are a lot of core members of the team as well who are going to be wandering around here. And let's build some really cool optimizations together. Thank you.